Hi again. In this video, we're going to look at permeability and water retention. And these are two more factors that affect the rate at which water will infiltrate into the ground and become groundwater. Okay, so we'll start with permeability. Permeability, if you look at the word, you'll notice that it ends in the word ability. Okay, permeability is just the ability of a fluid, and usually we're talking about water from precipitation. So it's the ability for water to get through a material. So you can see in this picture, there's some blue, which is, let's say it's rainwater or water from melting snow, and it is permeating, it's moving through the materials. Okay, so that's permeability. Permeability is not just based on holes, but it's based on how well connected those pores are. For example, if you look at the Swiss cheese up here, if I poured water into this hole over here, it's not going to be able to go through the cheese because that hole is not connected to any other holes. In this piece of pumice here, there are lots of little pores. There's a very high porosity, but the pores are not connected to the other pores. In fact, this is a drawing of what those pores look like in the pumice. So yes, there are a lot of openings, a lot of pores, but water can't get from one to the other. So the main factor that affects permeability is how well connected those pores are. If a material is highly permeable, it means that water is able to get through it quickly. So highly permeable materials have a high infiltration rate and a low rate of runoff, right? Because if water's getting in, then it's not staying on top. Now, certain materials are what we call impermeable, and that means that water cannot get through them easily. There are a number of factors that can create impermeable situations. So the two most frequent ones would be that the materials are either very tightly packed, like clay, for example, right? Clay is made up of microscopic particles. And so the smaller they are, the more tightly packed, the more smaller the pores are. So water has a really hard time getting through it. In the wintertime, ice can also make soil become impermeable. Because if there's water underground and the water freezes underground, it creates an ice dam, meaning that water can't get through it because the pores are clogged with ice. And then the third factor there would be packing. So we know that the more tightly packed soil is, the harder it is for water to get through because the pores are tinier and closer together. So humans, vehicles, animals, when we put weight on soil, we create more tightly packed grains, which leads to impermeability. Okay. Other things that are impermeable are things like parking lots and roads and sidewalks because water cannot get through them very easily. Okay. So let's look at a picture showing us what goes on underground, and we'll use some of these phrases in a true sense. All right. So we've got some houses up here sitting on a landscape, and we have a couple of wells. We have some aquifers. Let's take a look at what's going on here. So when there's precipitation, rain or snow or sleet, the water will infiltrate underground until it reaches an impermeable layer. Okay, so this layer here, this is all impermeable rock. What will happen is the water will then start to collect on top of that impermeable rock. And that's what allows us to dig a well, because we know that the water will never get through that impermeable rock. So as long as there's enough precipitation to keep refilling this, we're able to pump water out from the well. A spring is a very similar thing. In a spring, the water will go through the soil until it reaches an impermeable rock. With a spring, the water comes out on its own because of gravity pulling it down. Okay? So an aquifer is just a place where water gets trapped underground in large quantities. Okay. Now, permeability, unlike porosity, does depend on particle size. Because if soil has larger particles, it means it has larger pores, and water is able to get through them faster, right? If you think about this, if you're trying to walk through a room, if the room is very, very crowded and there's not a lot of gaps between the people, it's going to take you longer to get through. If the room is fairly empty, when there are large gaps between the people, you're going to get through it significantly faster. So we're going to look at a couple of animations to show this. So we'll start with this first one. So we have 4 containers of different size sediments. Gravel is composed of the largest sediments, so it has the largest pores. You can see these big spaces. Sand is smaller, silt is smaller, and clay are the smallest sediments. Okay, so they have different particle size. What we're going to do is when I push this button here, it's going to fill up each container with water, and it's going to show us how long it would take for the water to get through each of the different particles. So let's check this out. So the gravel, again, has the largest pores, and so it would take about 2 minutes for the water to get through it. The sand has smaller pores. It would take about 2 hours. The silt and the clay are going to take even longer because they have the smallest pores. In fact, clay has such a low permeability that it would take almost 200 years for the water to get through it. Now that's more than a human lifetime. So we say that clay is impermeable. In our lifetime, clay will not let water through it. Silt, you'd sit there and wait 200 days. Eventually it would go through. So it has a very low permeability. Okay. Now we're going to look at the same thing, but this time we're going to look at small particles, medium size, large ones. So these 3, they're all sorted, they're all round, and they're all the same shape within each column. Now we're going to look at an unsorted column. So let's see what happens here. So I'm going to push the button and the water is going to leave the columns. Okay, we'll do that one more time. What we see is the water made it through the large particles the fastest. The yellow particles were a little bit slower. The red particles were even slower. And something very interesting happened here. When the particles were unsorted, it took the longest and less water came out. And if you remember, unsorted particles have a lower porosity. So if we were to calculate how much water is in each container, this container here is able to hold the least amount of water because it has the lowest porosity. Okay, so now let's go back to this. So the other factor that we're looking at in this video is called water retention. And basically what that means is when water goes through particles, not all of it gets out. Some of it gets retained or gets trapped in the pores. And the way this one works is that if there are large particles with large pores, the water's going to easily get through it. So you're not going to have a whole lot of water retained or trapped in those pores. With smaller particles, there are smaller pores. So the water is more easily trapped in those small pores, so we get more water retention. So we're going to put all of this together. We're going to look at porosity, permeability, and water retention. Okay, so we're going to start with these 2 columns. They are filled with sediments. The sediments in this column have a 4 millimeter diameter. The sediments in the right-hand column have a 12 millimeter diameter. And so let's compare their porosities, their permeabilities, and the amount of water retention. So let's start with porosity. So what do we know about the total amount of pore space in particles with different size sediments? Well, hopefully you remember that particle size does not affect porosity. So both of these samples would have the same porosity. They would both hold the same amount of water. Now, how about permeability? Which one will let the water get through it faster? Well, we just saw that larger particles have larger pores. So water will get through them faster. It has a higher permeability. So if we poured water into both of these, it will get through the 12 millimeter beads faster than the 4 millimeter beads. And then as far as water retention, smaller particles have smaller pores, which therefore trap more water. So the 4 millimeter beads are going to trap more water and stop it from coming out. Okay, let's do one more. We're going to add even more to it this time. Okay, we're synthesizing. We're putting everything together that we've learned so far. Okay, so 4 different size soil samples. What we're going to do is we're going to drag each of these phrases and we're going to label them. And you feel free to draw this in your notes, draw this on a piece of paper, because we need to be able to know all of this. We need to be able to identify all these things. Okay, so let's start with permeability. Which of those samples would let water through the fastest? Biggest particles or the smallest particles? Well, biggest particles have biggest pores, which means water will get through them the fastest. So the 9/10 centimeter particles have the highest permeability, and the 3/10 centimeter particles would have the lowest permeability. All right, so now let's look at infiltration. Which sample is going to let water get through the fastest? Well, if something's highly permeable, it means water gets through it really fast. And if something has a low permeability, it will take the longest for water to get through it. All right, so let's do runoff next. Which container, if it were to rain, which would have the most runoff, which would have the least runoff? Well, runoff is when water stays above ground. So in which of these would most of the water stay above ground because it doesn't get through? Well, if the water gets in slowly, that means it's going to stay above ground. So the smallest particles would lead to the most runoff, and the largest particles would have the least amount of runoff because the water will infiltrate or permeate really quickly. Okay, how about water retention? So if we pour water in all these columns, which one would let the least amount of water through, or which would retain the most water? Well, small particles have small pores, so they retain the most water. Large particles have large pores, so the water will get through it the fastest, and less of it will be retained. All right, now we're left with one thing, porosity. I want to know which of these containers would have the highest porosity and which would have the lowest porosity. All right, so think about that for 5 seconds. So what do you think? Well, hopefully by now you really understand porosity, so you know that this is a trick, because you know that particle size does not affect porosity. So every single one of these containers has the same porosity. All right, so we are almost done exploring groundwater. Hopefully this video helped you understand permeability and water retention. I will see you tomorrow.